Hey guys, welcome to my YouTube teaching platform. Herein you can clear your basic concepts of physical chemistry, spectroscopy and quantum chemistry. If you are new on this channel, please subscribe and support me to help you in the best possible ways I can. In today's lecture, we will learn two important concepts, moment of inertia and degree of freedom. These two concepts are very important because in JAM, CSIR net, GAT and other competitive exams you will get questions from this part for sure. Therefore, we have to learn how to solve the numerical problems and what are the key points from where questions may be asked in our exams. So this unit of introduction to spectroscopy is the basis for your understanding the whole spectroscopy part. Those who are new in today's class, please watch my previous classes. The links for the same are available in the description box. So without any further delay, let us start today's class. The key important parameter we are going to discuss today is the moment of inertia of a molecule. The moment of inertia of a molecule is defined as the mass of each atom multiplied by the square of its distance from the rotational axis through the center of the mass of the molecule. Mathematically, it is given by I is equal to summation of mi ri square, where mi is the mass of the atoms present in the molecule and ri is the perpendicular distance of the atom I from the axis of rotation. The moment of inertia depends on the masses of the atoms present in the molecule and the molecular geometry. The explicit expressions for the moment of inertia of some common molecules are shown in this figure. In case of a linear diatomic molecule, if the axis of rotation passes through the internuclear distance, then the moment of inertia is equal to 0. But if the axis of rotation passes through the center of mass of the molecule, then the moment of inertia is given by I is equal to mu r square, where mu is given by ma into mb divided by ma plus mb, and it is called the reduced mass of the molecule. Now, in case of a linear triatomic molecule of type 1 as shown in this figure, where the rotational axis is passing through the atom B and the two other atoms are the same element A, then the moment of inertia is given by I is equal to 2 times of ma into r square, where r is the distance of atom A from the rotational axis. Examples of such molecule is carbon dioxide. But in case of a type 2 linear triatomic molecule, where all the three atoms are different, the moment of inertia is given by this expression, which is a bit complex. For non-linear molecules, the explicit expressions for moment of inertia will be different depending upon the axis of rotation that passes through the molecule. Now, let us solve a numerical problem based on the moment of inertia of a molecule. This is an important problem which was asked in degree level exam as well as in JAM and GAT exams also. The problem is calculate the moment of inertia of water molecule around the axis defined by the bisector of the SOH angle. The SOH bond angle is 104.5 degree and the bond length is 95.7 picometer. So let us solve this problem. To solve it, let us draw the water molecule as shown in the figure. The axis of rotation passes through the oxygen atom, and the distance of the hydrogen atom from the rotational axis is suppose RH, and the OH bond length is denoted by R, which is equal to 95.7 picometer. Now let this angle is phi, which is the half of the SOH angle and is equal to 52.25 degree. Now we can extract another figure from here for simplicity of our understanding. In this right angle triangle, we can write sine of phi equal to perpendicular by base, which gives sine of phi equal to RH by R. This implies RH is equal to R sine of phi. Now we know that I is equal to summation of mi Ri square. In case of this water molecule, I is equal to mh Rs square plus 0 plus mh Rs square. The mass of the oxygen atom makes no contribution to the moment of inertia for this mode of rotation, as the oxygen atom is immobile while the two hydrogen atoms circulate around it. So its contribution is 0. So therefore I is equal to 2 times of mh Rs square. This implies I is equal to 2 into 1.67 into 10 to the power minus 27 kilogram into R sine of phi whole square, where the mass of hydrogen is equal to 1.008 U, which is equal to mh equal to 1.008 into 1.6603 into 10 to the power minus 27 kilogram, which gives it equal to 1.67 into 10 to the power minus 27 kilogram, because 1 EU equal to 1.6603 into 10 to the power minus 27 kilogram. So therefore I is given by I equal to 2 into 1.67 into 10 to the power minus 27 kilogram into 95.7 into 10 to the power minus 12 meter into sine of 52.25 degree whole square. So this implies I is equal to 2 into 1.67 into 10 to the power minus 27 into 95.7 into 10 to the power minus 12 meter whole square. This implies I is equal to 2 into 1.67 into 10 to the power minus 27 into 95.7 into 10 to the power minus 12 meter whole square into 0.7907 whole square, where 0.7907 is the value of sine of 52.25 degree. So simplifying this, we get I is equal to 1.91 into 10 to the power minus 47 kilogram meter square. This is another similar problem which I am giving you as homework. The problem is calculate the moment of inertia of chloroform CHCl3 molecule where chlorine atom is labeled as 35 Cl around the rotational axis that contains the CH bond. The CCl bond length is 177 picometer and the HCl angle is 107 degree. Given mass of 35 chlorine is equal to 34.97 U. So to solve this problem, I am giving you this diagram as a hint. So I hope that using the concept of the previous problem, you can solve this problem also. So try to solve it. If you find any difficulty, then we will see it later, right? Now let us solve this problem 3. The atomic masses of fluorine and hydrogen atoms are 19.0 and 1.0 AMU respectively, where 1 AMU is equal to 1.67 into 10 to the power minus 27 kilogram. The bond length of SF is 2.0 Armstrong. The moment of inertia is, the options are here. This problem and many other similar problems were found in previous CSIR-UGC net exam. So let us solve this problem. Since HF is a linear diatomic molecule, so the moment of inertia is given by I is equal to mu R square, where mu is the reduced mass, and is given by the ratio of the product of the masses of the two atoms divided by sum of the masses of the two atoms. So mu is equal to mh into mf divided by mh plus mf. So substituting the value of mh and mf, and on simplification we get mu is equal to 0.95 AMU, and is equal to 0.95 into 1.67 into 10 to the power minus 27 kilogram, which gives us mu equal to 1.5865 into 10 to the power minus 27 kilogram. The value of R is equal to 2.0 Armstrong, which is equal to 2 into 10 to the power minus 10 meter. So therefore I is equal to 1.5865 into 10 to the power minus 27 kilogram into 2 into 10 to the power minus 10 meter whole square. So this implies I is equal to 1.5865 into 10 to the power minus 27 into 4 into 10 to the power minus 20 kilogram meter square. So on simplification we get I is equal to 6.3 into 10 to the power minus 47 kilogram meter square. Hence option B is the right answer. Again we have another problem from CSIR net exam. The problem is the C double bond O bond length is 120 picometer in carbon dioxide molecule. The moment of inertia of carbon dioxide would be close to, the options are here. The masses of carbon and oxygen atoms are given in the question. So to solve this problem, draw this figure in which the rotational axis is passing through the carbon atom in the CO2 molecule. The rotation of the oxygen atom from this axis, the distance of the oxygen atom from this axis is r, which is equal to 120 picometer. We know that for this type of type 1 linear molecule, I is equal to 2 into mass of oxygen into r square. So this implies I is equal to 2 into 2.5 into 10 to the power minus 27 kilogram into 120 picometer square. So this implies I is equal to 2 into 2.5 into 10 to the power minus 27 into 120 into 10 to the power minus 12 whole square kilogram meter square. This implies I is equal to 2 into 2.5 into 10 to the power minus 27 into 120 into 120 into 10 to the power minus 12 into 10 to the power minus 12 kilogram meter square. This implies I is equal to 5 into 14400 into 10 to the power minus 51 kilogram meter square. So on simplification we get I is equal to 7.2 into 10 to the power minus 47 kilogram meter square. So option D is the right answer. Right. So you try to solve this type of problems from different books you follow, and practice as much as you can, because in competitive examinations you must have to be smart in this type of calculations. Now move on to the next topic, classification of molecules. Based on the moment of inertia in three directions, or you can say in three coordinate axes, which are about the bond axis, that is the internuclear axis or x-axis, and the moment of inertia is denoted by IA. Secondly, the end over end rotation in the plane of the slide given by IB. And thirdly, end over end rotation at right angles to the plane of this slide given by IC. So depending on these three, the molecules are classified as linear, symmetric top, spherical top, and asymmetric top. Here in this slide you can see the moment of inertia in three directions. The first one is the rotation around the bond axis, and the moment of inertia is denoted by IA, in which the molecule is rotating along the x-axis. In the second figure, you can see that if the molecule is rotating along y-axis, then it will rotate this way in the plane of this slide. This is known as end over end rotation in the plane, and the moment of inertia is denoted by IB. In the third figure, if the molecule is rotating in z-axis, and it is called the end over end rotation at right angles of the plane of the slide, and the moment of inertia is denoted by IC. So if you can try to remember this chart, as you can see here, in case of a linear molecule, IA is equal to 0 and IB and IC are the same. Examples of linear molecules are HCl, oxycarbon sulfide, etc. Secondly, there are two types of symmetric top molecules, which are prolate and oblate. In symmetric top prolate, IB equal to IC greater than, which are greater than IA. For example, CH3F. While in case of symmetric top oblate, IB equal to IC is less than IA. Examples of such type of molecule is BCl3. Next is the spherical top. This type of molecule, the three different moment of inertia are same, that is IA equal to IB equal to IC. For example, CH4. The last one is the asymmetric top molecules, where all the moment of inertia in the three directions are not equal, that is IA is not equal to IB is not equal to IC. For example, water molecule, chloroethene, etc. I think if you can remember this chart, then it will be helpful to you to answer some conceptual questions. Okay. Now the next topic is degree of freedom. The degree of freedom of a molecule may be defined as the minimum number of coordinates required to specify the position of the molecule. Let us consider this molecule in space. So to specify the position of this molecule, we need the three coordinate axes x, y, z. Hence its degree of freedom is 3. Okay. There are three types of degrees of freedom: translational degree of freedom, rotational degree of freedom, and vibrational degree of freedom. The number of coordinates necessary to specify the translational motion of a molecule is called its translational degree of freedom. And similarly, number of coordinates required to specify the rotational and vibrational motion of a molecule is called its rotational and vibrational degrees of freedom respectively. In general, the total number of degrees of freedom of a molecule containing n number of atoms is thrice n. Okay. Now let us consider a linear diatomic molecule. So the total number of degrees of freedom is equal to 3n, which is equal to 3 into 2 equal to 6. Since it is diatomic, so n equal to 2. Now to describe the translational motion of this molecule, we need all the three coordinate axes x, y, z. So the translational degrees of freedom is equal to 3. But to specify the rotational motion, we need only x and y axis. So the number of rotational degrees of freedom is equal to 2. As you can see here in this figure, the molecule may rotate along its internuclear axis or the x-axis this way, or it may rotate along y-axis in the plane of this slide. Okay, so therefore it has it required two coordinate axes x and y to specify its rotational motion. So the number of rotational degree of freedom is 2. Therefore, the number of vibrational degrees of freedom is equal to 6 minus 3 plus 2. 3 plus 2 is the number of translational plus number of rotational degrees of freedom. So this equal to 1. Okay, and we know the total number is 9. Out of 9, total number is 6, and out of this 6, 3 translational, 2 rotational, and 1 vibrational degree of freedom. Now, in case of a non-linear triatomic molecule, the total number of degrees of freedom is equal to 3 into 3 equal to 9. Okay, and the number of translational degree of freedom is 3, since we need all the 3 coordinate axes to specify its translational motion. Now let's see what about the rotational degree of freedom. The non-linear molecule can rotate about the x-axis as shown in this figure. It may rotate along y-axis like this in the plane of this slide, this way. Also, it may rotate along z-axis about the plane perpendicular to the plane of the slide, this way. So hence we need all the 3 axes to specify its rotational motion. So the number of rotational degree of freedom is also 3. Therefore, number of vibrational degree of freedom is equal to 9 minus 3 plus 3, which is equal to 3. So it has total 9 degrees of freedom. Out of this 9, 3 are translational, 3 rotational, and 3 vibrational degrees of freedom. Is it clear? In general, we can have a formula for a linear molecule containing n atom. Total degrees of freedom is equal to thrice n. Number of translational degree of freedom equal to 3. Number of rotational degree of freedom is equal to 2, and number of vibrational degree of freedom is equal to 3n minus 5. Okay. On the other hand, for a non-linear molecule containing n atoms, total degrees of freedom is equal to thrice n. Number of translational degree of freedom is equal to 3. Number of rotational degree of freedom is equal to 3, and the number of vibrational degree of freedom is equal to thrice n minus 6. So take this as a formula, and using this formula we can find out the number of degrees of freedom in any kind of molecules, provided its shape is known. Okay, I think we have left out one topic from our syllabus, that is the selection rules, but already we have talked about the selection rules when we discussed the factors that influences the intensity of the spectral lines. So in that class we have discussed that the spectroscopic transitions are governed by some rules known as the selection rules. The selection rules are for different types of spectroscopic studies are different, and the selection rules are actually determined by some quantum mechanical calculations. So we will discuss the specific selection rules for a particular spectroscopic studies when we study them in details in the next units. So if you have any queries related to this unit, introduction to molecular spectroscopy, then please give your comments in the comment box, and if you have any questions, then feel free to ask them. So I think I have covered all the topics from this part, so I will be waiting for the feedbacks from you. So this is all about today's class. See you in next week. So till then, enjoy learning. Bye bye.